All right, thank you all very much for coming today, and thank you to Mike, Kwame, and the organizing committee for inviting me here. This is actually my first time in Rolla, and it's a great trip, so I've enjoyed it so far, and hopefully we have a good talk. For those of you who may not know, Mike and I have known each other for almost 20 years now, and Mike tried to recruit me as a PhD student, and I said no, right? It's still bitter. If I can provide some background, so my girlfriend, who's now my wife, implored me to stay at Virginia Tech, which I did, and it was a better decision. Sorry, Mike. You may be an attractive metallurgist, but not too attractive. Looking today, so my talk is titled From Brutal Facts to Sustainable Solutions, and we're going to dig into this a bit, but before we get started, you'll see a bit of a dual role. I'm actually serving in two positions now. One is Department Head of Mining and Minerals Engineering, which is my kind of academic background. I'm also serving as Department Head of Material Science and Engineering as well, and I don't wish that upon anybody, but this is an interesting topic where we can kind of commingle those a bit. So setting the stage for the talk, last year I read this book by Jim Collins. So being in a dual role, I felt like I needed to know a little bit more about organizational leadership, and I think this is a real classic in most MBA programs and most management consulting. It's called Good to Great, and in it, Jim really laid out a pretty rigorous methodology for identifying companies that had gone from average performance to exceptional performance. And then after doing that, he went and looked at those 12 or so companies, and this was over a 150-year time scale. He found these 12 companies. He really looked in detail, him and his team, at what made them distinctive. And then he provides guidelines for how we can do that in our organizations. And I looked at this and actually thought this was a good notion of how we could build a research strategy. And there was one chapter in it that really stood out to me, and it's kind of what drove the title of this talk. I'll read this one. This one's a text-heavy slide, but I'll read it. He said, "Every good to great company faced significant adversary along the way to greatness in one sort or another. In every case, the management team responded with a powerful psychological duality. On one hand, they stoically accepted the brutal facts of reality, and on the other, they maintained an unwavering faith in the end game and a commitment to prevail as a company despite the brutal facts." I think a lot of time when we're developing R&D and we're looking at R&D, we start with the green text. And we start with this unwavering faith that our ideas are going to be exceptional, they're going to push the boundaries, they're going to change the game. But we've not done that without first accepting the brutal facts of what the situation is, what are our boundaries and constraints. And I know when I first got into critical minerals research, this is what happened to me, right? I was a young, untenured faculty, very gung-ho, got into a lot of things, had really cool ideas, and very quickly realized not many of them were very practical and very few were economic. So with that, I think as we think about critical minerals, we really want to first look and have a good appreciation for those brutal facts, and that's what we'll do today. So in guiding the presentation, I'm going to start by talking a little bit about some motivation and scope. Then we'll get into the middle part of the presentation, which is titled Brutal Facts, where we're going to look a lot in the rare earth markets, and I'd say this presentation is really focused on rare earths. And so we'll look at rare earth markets and kind of see what some of the headwinds that we're facing. And then through that, we'll see if there's pathways for sustainable solutions so we can maintain that unwavering faith. Mike and I did coordinate slides, and I think there's only two that overlap with Mike's presentation, and you'll get to hear my spin on those as we go through. So I always like to start any talk about mining, and when I teach undergraduates, I always start with this slide, which if you go search the UN Sustainable Development Goals, this is the picture that will pop up. And I like to articulate this as, sometime in the 2010s, a lot of people a lot smarter than me got around a table and said, what are the really great things we want to do as society? And if we could do these things, we would say we made it, as a global society. And these are things like no poverty, zero hunger, affordable and clean energy, right? Really good things we can universally agree to. This is what you get if you Google UN Sustainable Development Goals. This is actually the version of the picture I like to show, because this one really, really articulates how mining fits into that. And you can kind of see the mining logo in the middle, and then the wedges going around, the larger wedges are ones where mining has a really direct impact on our ability to achieve that goal as a society. And I think if you count it up, it's about 11 or 12 out of the 17 mining is absolutely critical for. And if you think about that and you compare that to other industries, right, and you think about communications or tech industry or financial services, mostly they're going to have impact on a couple, right, 3, 4, maybe 5 goals. Having impact on nearly like 3/4 really speaks to how central our industry is to all that we want to do. Tying that to something a little bit more tangible, right? And I think Mike showed some numbers, and he asked us to do math in our head, right? I like to show this in a bit more tangible way. And this is like saying, hey, where are we going in society, and how much material are we going to need to get there? And this one shows kind of the exotic metals or technology metals in a conventional car versus an electric car. And there's 2 things to take note here. One, if you look at the electric car bar, it's a lot more colorful, right? And this is a Virginia Tech orange and maroon themed theme bar. It's a lot more colorful, meaning there's a larger diversity of metals going into these new technologies. It's also 6 times longer, right? So the amount and the type of materials that we need to do the great things we want to do in society is increasing in complexity. Interestingly, you could say the same thing about energy. And I read a news article a couple weeks ago, and they talk about we like to project in our heads that new technology will require us to use less energy, but most of the major innovations, right, have actually required us to use more energy. And it's like initially you can see this high ramp up, and then you may see some efficiency. But whenever some new technology comes into society, a very disruptive technology, you see an increase in material needs, an increase in energy needs. And I think AI is the quintessential example of this right now, and we're all going to see where this goes. This is one that we've seen a lot, but I like to show this to contextualize it as well. This is from the International Energy Agency, and what they show on the left side is who controls the extraction of certain mineral and fossil resources, and then on the right, who controls the processing of certain mineral and fossil fuel resources. And what I think they did here that was pretty clever is obviously you can see down at the bottom they've got rare earths and then some battery and other electric materials, and at the top they've got oil and natural gas. I think if you go talk to anyone on the street, there is universal recognition that fossil fuels are a geopolitical commodity, right? And it's like constantly pushed, and there's like universal acceptance in the public with that. And I think we're just now getting to the point where we accept that with our mineral resources. I think when this was first published, it was 2019, and I noticed even talking to students and parents, and you try to talk about, hey, critical minerals, and these things are important, and they're very, there's a dominated supply chain. Those conversations were difficult to have because people didn't have just the basic background knowledge and nomenclature. I think in 2025, that has changed dramatically. And when I talk to students and parents, they come in with some pre-knowledge of this. So I think the work that we're doing collectively, as a community is working, but we need to do more of it. Like I said, I like to focus on rare earths. We have 60% of the mining is done in China, and then 80 to 90% of the processing done in China. I think there's no surprise there. This was one of the slides that I copied from Mike's presentations, and then I actually did put the equation, right? He talked about the multiply the 3 numbers and take a geometric mean. As a professor, I'm still at the stage I got to put an equation in somewhere in the presentation. I like showing this, though, because this is a pretty typical, we would call it like a risk tracking plot. Right? So on one axis, you have what's your likelihood of impact, and on the other axis, you have what's the disruption potential if you do have an impact. And that's kind of the way this is formatted in the criticality plot. But the real advantage of a criticality plot is not to show you, is not only to show you where you're at and where you stand with respect to risk, but how you can formulate strategies to mitigate risk. And so I imagine, and I think DOE's been very good about this, and I imagine they use plots like this to develop their mitigation strategies. 2 that jump right off, right? If you want to reduce economic vulnerability, you would develop substitutes, right? So if we can develop a magnet that doesn't require dysprosium, then the economic vulnerability we have to dysprosium goes away. And so that's how you would reduce on the y-axis. The x-axis, you would diversify your supply chain, right? So if you still wanted magnets that had a lot of dysprosium in them, and you want to reduce your disruption potential, then you find other sources of dysprosium. I like showing it this way because this is what connects my day job and my night job, right? My day job in mining and minerals engineering is all about diversifying supply, how we identify new resources, how we identify ways to process and bring those resources online. And my night job as material science department head is how do we design new manufactured goods that use less materials and less of certain critical materials. And so I think there's a way to synergize those, right, if we can get the right teaming and the right partnership to work in tandem, right? And I always ask the provocative question, right? I think we are, we're on the boat now and we're trying to bail ourselves out in this mineral criticality issue, right? I think we're heavily exposed, so we're trying to bail out. But how do we look forward and say what's going to be critical in 20 years, in 30 years, in 40 years, and develop frameworks that prevent us from needing to have this discussion in the next generation, right? We're having the discussion now. How do we develop ideas that are going to get us away from having to have this discussion in the future? I think it's an interesting idea. I think it's aspirational, but I think it's something we should keep in mind as we solve the challenges right now. And this is another one I think Mike showed, and I like to point this out. So I always heard this called the Wheel of Metal Companionality, which I thought was a pretty good title to it. And as he pointed out, this shows like each wedge of the pie is one of the major elements that's produced. For instance, here you have titanium in the top right. That's one of the major minerals that's produced. And then along the periphery of that, you have the secondary or minor metals that are produced as a byproduct of titanium production. And then the way this one's drawn is how far closer it is to the center indicates how much of that metal is produced as a co-product or a byproduct from the primary metal. So gallium, for instance, is almost at 100% of the aluminum. It's almost at the middle of the aluminum slice, meaning that almost all the gallium is produced as a byproduct of aluminum smelting. And one thing I like to draw out here, and the differentiator, I think Mike had cobalt, nickel, and gallium circled on his. I've got all the rare earths circled on mine. And this kind of points to why I think rare earths are so interesting, right? If you look uniquely, they have high geographic concentration, both in terms of the resource and the processing capability. This plot would show us that they have very low association with a major ore. This is showing, I think it's the 10% range of in the titanium slice. So you may have some rare earths coming from monazite, which is a byproduct of titanium production, but it's pretty minimal, right? You have almost no end-of-life recycling. I think if we look at any recycled good containing rare earths, we'd say it's almost negligible in the scope of the rare earths we need. And the last one I'd add on here is that rare earths tend to be used in applications with very, very high qualification standards. And we talked about, I think there was a question about off-takers that was given to Mike. We've talked to some of these off-takers, and many times they will not even tell you what their qualifications are unless you're under NDA. And then when you're under NDA, they do not want you talking at all about them, right? Because they're very afraid of their supply getting restricted because they're even in discussions with potential other suppliers. It's a very, very challenging environment, and I would not underwrite this very, very high qualification standard that's required for rare earths. So together, I think these factors really say, hey, this is something, it makes them a really interesting case study for targeted efforts in supply diversification, which has really been a big focus of, I think, DOEs over the last decade. And certainly my research, we've looked at how we diversify and create new processing technologies for rare earths. So that's kind of the overview of the scope, right, and why we think rare earths are interesting and why we look at them. Now we've got to lay out some brutal facts of what you got to appreciate if you're trying to develop a rare earth process. This right here is probably my favorite plot in the entire presentation. And I'll walk you through this and some of the implications of this, but it's one I spent a lot of time thinking about and really deliberating on because it's so simple, right? What's being plotted here is actually very, very simple, but the implications become very, very significant. And so this is done by the INMIC group at USGS. They produce all the statistics, production and use on mineral commodities. And what they did here is they just took every mineral commodity that they track, and they plotted its nominal price per ton on log scale versus the global production on log scale. And then if you multiply those two, you get lines of constant market capitalization, is the way to think about it. So if we multiply tonnage by price, we get how much that value is in terms of commodity. And I like to look at this, and you can see in the top right, you've got gold, copper, aluminum, and iron. These are all 100 billion plus markets, right? But from a total value, there's not much difference, which is pretty interesting. There's not much difference between gold and iron ore. They're just on very, very opposite ends of the value tonnage proposition. As you work your way down, right, you go from 100 billion, 10 billion, 1 billion. You can see a lot of the critical minerals, and especially the rare earths, are in the tens of millions to $100 million of total market capitalization. Samarium is less than 10 million. I would wager there's several people in the room that could probably buy the global supply of samarium with a retirement account today, right? Like, it's not that much money, and you could control all the samarium in the world at any given time. But the problem is this creates trouble when you take it to the investors, right? And we say, hey, we need $500 million to build a rare supply chain, and we're going to get a market that might be, tens of million dollars a year. The math just doesn't work out, right? It creates a very, very challenging investment scenario. This also feeds into how process innovation works, right? And I talked to people at the major equipment producers that have massive R&D teams that really try to push innovation in markets, and all of their innovation is going into gold, copper, aluminum, and iron, right? And I wonder why. And they do very, very little in the rare earths. And so it's interesting because on a commodity basis, it's not that valuable, but then the technology that's enabled from their production, that's where all the value is. But I think this kind of speaks to why we have a critical minerals challenge, because in many cases, we're talking about markets that are in the hundreds of millions of dollars, and we need tremendous amount of CapEx to be able to develop a supply chain. It really turns us upside down on how we would get there. So with that in mind, that's kind of the macroeconomic perspective. Microeconomics, one of the things I did, this is about 3 years into my rare earth journey, I realized I needed to know more about what I would call the background data, right, to understand what the available resources look like. So therefore, if we were trying to propose a new unconventional or novel idea, we would be able to tie it back to what could be achieved if we wanted to go out and mine rare earths. So I did a study, and I wrote a book chapter in this book you can see there. And what I did is I looked at all the NI 43-101 reports published on rare earths over about a decade time scale. And you can see the map there that contains some of these projects. And then I laid them all against a common economic model, so we could see what their fundamental economic proposition is for these. And so out of them, 21 projects had data where you could extract an economic model, all showed really, really positive results, right? We're talking like 30 to 50% rates of return in some cases. Head grades in the 1 to 2%. And these are ore deposits, like rare earth ore deposits all over the world. But out of all these, not a single one was brought into production. And why did that happen? And as we know, in the mid-2010s, we had this like price inflation of rare earths. Many NI 43-101s will use a 3-year rolling average on their price for their price deck. So they had kind of these overinflated prices in their economic models. And if you fast forward to like 2019, 2020, none of those projects were profitable. Now, I've got a slide in a second that shows that. But here, I thought this was interesting. These are some plots from the book chapter. So on the left, you can see the CapEx curve. So this is the capital cost to bring the mine into production versus how much production you get. On the right, you see the OpEx curve. Here's another way of showing that. So this is like a capacity curve or a supply availability curve. So you can see the width is how much production capacity that mine has, and the height is what the operating costs are. So if you read this, you can say, hey, you probably need to be in the $10 to $20, $30 per kg rare earth production cost if you want to be able to compete against these mining projects. And so here's another way of showing that. So what this has is the dots are the y-axis is the basket price. So essentially how much revenue you can get from operating that mine. And the x-axis is how much it would cost, both normalized to a per kilogram product basis. And similarly, you can draw these lines of constant margin. And you can see some look really, really good. Like you're making $75 a kg margin on 120 kg revenue. That's like more than a 50% net margin. Like that's incredibly good in commodities, right? And even in the worst case, you're at like a $25 per kg margin. Anybody would build these, right? These are very, very good numbers. You would want to do this. The problem is that's what was reported in their NI 43-101s. When you lay these against a common economic model, they all pretty much become submarginal, right? They all hit right at the break-even line. And so I like to say it this way, right? If I were wanting to set the prices to a level that would make all of these unprofitable, these are the prices I would set them to, right? It's like I'm almost trying to do a line of best fit through the break-even point, and then it's like that's not what I did. That's what the data said, but you could almost draw that line of best fit, and it hits right at that break-even line. So with that, if we want to try to develop sustainable solutions, we have to understand the cost proposition and the economic headwinds you face are very, very significant, right? These are mines with 1% to 2% head grades, and they are not profitable under today's scenarios. So if you're going to go look at unconventional resources, stuff that's very low grade, hard to process, you've got a very large uphill climb to make before you can get to something that's going to be able to compete against what's out there. But there are some gaps of I think, really positive light here. And here's one I like to show because I think it really brings to light something Mike implied in his presentation. This is focusing solely on terbium and dysprosium. So we like to think a lot about rare earths and aggregate, but I really think we've got to change that and look specifically at magnet critical rare earths, and then even more specifically at terbium and dysprosium. So this is a slide that Aclara put together. Aclara is seeking to develop a heavy rare earth deposit in South America, and they went and looked at all the different sources of terbium and dysprosium and kind of put this together on a waterfall chart, right? So the 2023, the total supply is about 3,400 tons. Not very much, right? We go back to think about that market. Not very much, 3,400 tons. About 3,300 of that is processed in China with a little bit of capacity from MP and Lynas and some others. If we look at where we need to be in a decade, that's where we need to be to meet the production targets around energy and defense technologies, right? We need to more than double the size of the terbium and dysprosium market, up to about 8,000 tons per year. And that's a projection by Argus. I think if you look at Benchmark, if you look at Adamas, they all show these similar plots of this incredible demand. Some of it's cooled in the last couple of years, but you still see a lot of demand. And then if you also look at any of those, there's this big gap, right? And they say, okay, here's some places we know we could probably get it, and about half of it, we have no clue where it's going to come from. And I think this is a really, really big opportunity to say, even with the Chinese resources and other global resources, we're still probably not at a point where we'll be able to fill the gap. And you can imagine that's going to lead to some price corrections and things like that. But I see a huge opportunity if we can get there in terbium and dysprosium and really think about that and how we can work on the technology that's going to be needed to deploy that. So in our research, we kind of take that approach. So we take this stoic fact perspective and understand a lot of what we're going to work on probably won't be economic, right? And I'll be the first to tell you, we spent many years looking at coal refuse as a potential rare earth source. It's very, very tough, right? Like, it's very tough to take 300 part per million rock and make an economic case out of it. And so it's like, I've done those calculations, and I'll be the first to tell you that. But I think it doesn't stop there, right? I think that's a part of it, is how do we think about unconventional resources, but use that and marry that with a way that we can develop innovative processes. And I like looking at unconventional resources because there's no textbook on how to go recover rare earths from coal refuse, right? I can't go find that in my mineral processing textbook. So I have to challenge my assumptions, and I have to really think deeply about how we design processes. And through that, we uncover really cool things. And maybe things that aren't necessarily, they're relevant to coal refuse, but they may be relevant to other mine tellings. They may be relevant to other, areas where there is potential, right? And so these are just some examples. I threw some up here, the things I've been fortunate to work on. So things like phosphogypsum, mine tellings, even municipal solid waste ash, acid mine drainage. I know my colleague Winsai Zhang is speaking right after me, and he's going to talk about a lot of these, so I'm just teasing it up for that. And then here are some of the processes we come up with, fine particle separations, novel extractants, circuit modeling, those type of things. But I really want to drive this home. I think the real benefit and the real mission that we've been able to accomplish is helping to rebuild the human capital, right? And we like to say we're mining for talent. So the technology that we produce and the resources we produce, I think, are one outcome, but the really, really beneficial and the really critical outcome is the talent that we're able to produce. And we've got graduates now working at MP Materials, working at battery recycling facilities, working at people developing lithium deposits. And I think that's been a real advantage and a real benefit of working through the university is we do have this capability, and we can really drive home this connection of resource, process, and talent. Another thing I'll put out there is I think we may need to rethink the way we look at mining and the mining value chain. And I've shown this for coal, right? And this is kind of where we got started is in coal. But you could take this, don't let coal turn you off. You could apply this to any mining value chain. You start with a coal mine, you may go through a processing plant, and then nearly all of the carbon you produce goes to generate power. You'll have some of the residue that goes to a fly ash pond. Maybe there's a way to valorize that through like cement additives. You might have some going to metallurgical applications, but there's really only one or two major value chains. And I contrast this to our colleagues in the petroleum industry, right? Which they've really, really mastered the way to squeeze every ounce of value out of a barrel of crude, right? It's like they get value out of every hydrocarbon that comes up out of the ground, and they've really, really mastered that down to producing asphalt with all the residue, right? And in the mining industry, I don't think we've had that paradigm of like, hey, once we move a ton of rock, we should squeeze every bit of value out of it. And so I pose this as like, hey, could this be the next generation mining value chain, right? Where we look at all the different ways we could possibly generate value from that. Everything from how we integrate water treatment and environmental remediation with value recovery. How do we stop thinking about coal necessarily as a value source, but as a carbon source? And is there a way to derive premium carbon products from it? Right? This is what the petroleum industry did. They derived plastics from hydrocarbons, right? Can we even look at our legacy waste and extract value from that? And so I show this as a thought exercise, but we've done a number of projects. I could go circle a number of projects we've done around this, but I would encourage all of us in the mining space to really think about this and really think about that notion of squeezing every ounce of value, because that's how we're going to change those cost curves and really prevail against those brutal facts. So in closing, 2 points I want to make, and I knew Mike was going before me, and I wanted to provide one for perspective, because when I was a very young, untenured assistant professor, Mike asked me a very good question, and he may not remember this, but it's like, why do you want to work in critical minerals when 99% of your graduates are going to get jobs elsewhere? Right? He's like, they're going to be working in iron and aluminum and all these things. And you've seen this plot before as data, but I think it looks good as a picture. This is the amount of material that's mined per year for these different types of materials, right? And so you can see, and I can't even show crushed stone on here because it would overtake the whole graph. But you can see where, in terms of volume and amount of material, where the behemoth is. Really, the technology metals, they're the spices in the cake, right? Like you don't go add 2 pounds of cinnamon to a cake, you add just a teaspoon. And that's the way these rare earths are. They're just a little bit of spice that goes into society, but they bring out all the flavor. And then the other one, like I said, I work at a university, and I think this notion of rebuilding talent is absolutely critical. And this is something we take very seriously at Virginia Tech. We've done a couple media releases. One we did last summer on the right was interesting. We pulled in interns from across all of the engineering disciplines and had them work on critical mineral projects for the summer. So we had chemical engineers, mechanical engineers, systems engineers, mining engineers, metallurgical engineers, all working together on the same projects. And then that proved very, very fruitful. And now many of them are pursuing jobs throughout the mining and mineral space. And so with that, I have 2 minutes left. My name's Aaron Noble. It's been an absolute pleasure to give this presentation, and I look forward to seeing you guys later in the day.